Now, moving ahead, we will now begin with the second technical session of the day. Our resource person for this session is Dr. Arijit Baral, sir, has joined us. A warm welcome to you, sir. Dr. Baral is currently serving as an associate professor in the Department of Electrical Engineering at IIT Dhanbad. He completed his BTech in Electrical Engineering at the West Bengal University of Technology, followed by an ME in Electrical Engineering from Bengal Engineering College, Shibpur, and later completed his PhD in High Voltage Engineering at Jadavpur University. During his academic journey, he secured the first position in the order of merit at both the undergraduate and postgraduate levels, and received the Inspire Fellowship from the DST, Government of India, as well as the prestigious Power System Operation Corporation Award in 2015. He was elected as an Associate Fellow of the West Bengal Academy of Science and Technology in 2021. And he was also enrolled as a senior individual member of the Indian National Academy of Engineering in 2025. He is also a member of SIGRI India. Sir has authored numerous research papers in reputed peer-reviewed journals, including 34 papers in IEEE journals, supervised 8 doctoral students, and holds 4 patents and 1 copyright. He serves as an associate editor of the IET, High Voltage Journal, and is a member of the editorial board of scientific reports published by Springer Nature. His specialization includes condition monitoring of high voltage power equipment. Sir will be speaking on the topic condition monitoring of power transformers for efficient and sustainable energy. Sir, we request you to kindly take over the session. Thank you.
Is my voice audible?
Sir.
Thank you for that lovely introduction. So, can I share my screen so that I can start with the PPT?
Yes, sir, sure, please.
Okay. I think it's visible, right, from your end?
Yes, sir, it's visible.
Please confirm whether the slides are changing at your end.
Yes, sir, yes, sir. It's changing.
Okay.
Yeah.
Okay. So, good evening, everyone. I'm sincerely sorry for disturbing you at this hour, but unfortunately, I couldn't manage earlier time slots, so I had to take this session. So, the topic of my lecture is condition monitoring of power transformers for efficient and sustainable energy infrastructure. Now, typically, if we deal with condition monitoring, we do not associate with efficient energy usage or sustainable infrastructure. We generally use it for maximizing asset utilization. But if we look into it in a deeper sense, we will see that if you actually commission a large power transformer, for that matter, we actually use considerable amount of energy in actually constructing all the components that a transformer needs. For example, if you need a 100 or 200 MVA transformer, later on I'll give you a brief details about how much carbon dioxide equivalent is actually generated for manufacturing a reasonably large power transformer. But for the timing, bear with me. So if we consider manufacturing of a new unit, you need steel, copper, insulating oil, cellulose. And if you are considering condition monitoring for delays or premature replacement, you need the raw material to be extracted from the existing unit, and you also need some kind of transportations to install it at the site, because it's quite obvious that you are not going to manufacture the equipment at the site. So you are going to manufacture the equipment in a factory, and then you are going to transport it to the site, and in the process you will also contribute to carbon footprints. So the obvious way to decrease this carbon footprints, which deals with either manufacturing and installation of a new power transformer or decommissioning and dismantling of an existing unit, if we can extend the remaining useful life of an existing in-service unit, via different suitable preventive actions, then that will reduce the overall requirement of this metal as well as the carbon dioxide emission as per the life cycle assessment database. So this is just a small example about how much carbon footprints or carbon dioxide is actually generated or equivalent amount is generated if you want to manufacture two reasonable size power transformer. So in this table is actually taken from a journal paper which is published in Energies. The DOI is given over there to cross-ref it. So you can see that if we consider all the equipment that are needed, for example, steel, copper, cellulose insulation, mineral oils, and other materials, so the equivalent amount of carbon dioxide in tonnage is significant. So we are talking about a small power transformer. If we are going for a larger transformer, for example, 100 MVA or 200 MVA, it will be even more severe. To reduce the overall impact, as far as the CGRE commission, CGRE A3B3 colloquium is concerned, they have proposed a diagram which basically is shown on the right hand side of the slide, which shows how you can reuse or recycle the material which has been extracted from a unit which has reached the end of life. But here lies a catch. What about the material which cannot be recycled and reused? For example, if you're talking about solid material, solid insulating material, kraft paper, press board, so on and so forth, and also liquid insulation to a certain extent, they cannot be reused to the fullest extent. They must be disposed somehow, and that creates problem, environmental impact also. So you can see that if you look at the right hand side table, look at the last two entries. Oil, which can be recycled or reused, approximately about 70 to 90%. But insulating paper or press board can only be recycled at maximum about 50%. So rest of it has to be disposed somehow. So the obvious way is either to use it as landfill or to incinerate it. Either way, it is going to create an environmental impact which needs to be reduced. So if you do not dismantle a unit and thus can avoid the requirement of recycling, reusing, or using the material which cannot be recycled as landfill, or if you delay the overall end of life criteria of a particular unit which is in service, then these impacts can be reduced to a considerable extent. So this brings us to how we can actually make more energy efficient infrastructure and how we can make the equipments more sustainable in nature. See, energy efficiency can be increased by reducing these hidden energy losses. These losses will always be there, whether you are talking about a medium-sized transformer, dielectric distribution transformer, or a power transformer, that for that matter. Obviously, the amount will be different, but what is important over here is that these hidden energy loss will increase over time. The dielectric loss, as the insulation ages, it will be more leaky in nature. The leakage current is going to increase, the partial discharge activity is going to intensify, and so on and so forth. So if these hidden energy losses can be detected earlier during its operation, and then we can identify proper steps or take proper necessary steps to reduce these energy losses in the process, so we can make the overall infrastructure a more efficient in nature. Please remember that we are not talking about hidden energy losses for a single unit. We are talking about large number of power transformers and other such large power equipments which is presently connected in an entire grid network. Yes. Is my voice audible? Yes. Okay. So if you can detect these losses at an early stage and you can prevent the loss escalation, so we can basically save lots of energy per year. Not to mention, we can also reduce to a significant amount the energy, the environmental impact that dismantling such a large unit will have. So this brings us to what can be the preventive measures or what can be the steps that should be taken to increase the remaining useful life of our existing infrastructure, delay the commissioning of a new unit, or to delay the dismantling and uh, incineration of cellulose material altogether. So these can be done by tracking or rather preventing transformer failures, which can cause oil leakage into soil and water, fire or toxic gas release. Because see, the mineral oil that we use in a transformer, it has a high flash point and boiling point, but it is still flammable in nature. If due to some fault this temperature is reached, then essentially the oil fumes spontaneously catches fire and it essentially explodes. There are many videos available in the public social domain, so you can search them. If a transformer, particularly a oil field transformer, catches fire, it is a very serious issue. So this will create toxic gases and fire hazard. And long outage, obviously, if a transformer is down for a large amount of time and you don't have plan to replace it using a new equipment to maximize asset utilization, obviously you will have to resort to some other diesel generator, because you cannot deprive the customer beyond a certain point. The continuity of electric power needs to be maintained. So what is the plan behind all this delaying of dismantling, increasing of RUL, so on and so forth? So what can be done? We can basically track these three parameters: moisture ingress in solid and liquid insulation, partial discharge that will be present in the solid insulation, we can track them, and oil degradation. Now, these parameters, though it looks very simple, if you're talking about a large transformer, there are several factors which will come into play, and I will be actually explaining how these determination of these factors becomes difficult. So this brings us to what transformer insulation diagnosis is all about. Because if we can diagnose a particular equipment insulation and we can predict reliably, so this is the problem that is going on with this particular transformer. We need to fix it fast, otherwise it will escalate to a larger problem. In order to do that, we carry out certain tests. Depending on whether the test requires complete shutdown of the equipment and isolating the equipment from the grid and thereafter testing it in an isolated manner, or whether the equipment can continue to run and we can do the measurement, depending on that, we can either do an online test or an offline test. Now, online test, an example of that, which we will be dealing in later in the PPT, is basically dissolved gas analysis. So what we do, we open up the oil bulb, which is present in the bulb oil tank. Then we sample out a small amount of oil. Then we test it. Remember, we only find out what amount of dissolved gases and which dissolved gases are present in the oil. We need to interpret these compositions of gases to identify what is wrong with the transformer. And there are certain offline tests as well. Now, see, it appears that if there is a test which can be performed online, why go for an offline test which requires shutdown of the equipment in the first place? Because if you are shutting down a power transformer, that means in a ripple effect, all the transformers and loads connected down the line will also get affected. So we should be always resorting to online test. But the problem is online test can only give you certain information, and certain crucial information cannot be obtained using these online tests. For that, offline tests are required. So you cannot totally avoid the offline test. However, due to the advancement of recent machine learning algorithms, we can opt for a digital twin where an offline test can be replaced by its cybernetic counterpart. But more of that later on. So the first thing that we are going to deal with today is condition monitoring of oil. So if we look at this particular chart, in total, there are 6 types of fault that can be categorized as incipient faults. Incipient faults are small faults that the transformer can work with. That means the fault is actually present in the transformer and it is continuously creating energy loss, but it is not a major fault, and hence the transformer can work even when these faults are existing. So these are discharge faults, which can be again subdivided into D1 and D2. Thermal fault, depending on the temperature, I will show it later on. Depending on the temperature, there are 3 types of thermal fault: low temperature fault, medium temperature fault, and high temperature fault, and partial discharge. Now, if you look at this particular chart, you can see that depending on the temperature, different type of gases actually gets evolved and remain in dissolved state in the oil. Remember, we are talking about online tests, so we are not shutting down the equipment. We are only sampling out a small quantity of oil and then we are testing it. The equipment which is required for identifying which gas is present in which quantity. By the way, dissolved gas analysis gives us gases in ppm, parts per million. You need what is known as a gas chromatographer. It's a costly equipment, but it will provide you the details of all the gases that will be present in the oil. The problem with this kind of analysis is that if suppose instead of, I told you that there will be 6 types of fault, each fault will be actually accompanied with generation of few specific gases in specific proportions. But the problem is, if multiple incipient faults exist in the equipment, then it becomes very difficult, because each of these incipient faults will generate its own gases, and the resultant gas composition that will be present in the oil will be ultimately identified by the gas chromatographer. Remember, I told you that the interpretation needs to be done at the user end. Gas chromatographer only will give you the gas compositions, so it becomes very difficult to identify which faults are coexisting together. Nonetheless, it will actually help you in identifying minor faults which may in the future get manifested into a larger problem. So if you look at this particular graph or chart, you can see there are 1, 2, 3, 4, 5, 6 major gases mentioned over here. But if you actually go for gas chromatography, you will get not these 6 gases, but different many gases, around 10 to 12 gases. Okay, out of this, depending on which particular interpretation technique you are using, you will be either using these 6 gases mentioned over here or certain subset of the gases identified by the gas chromatographer. Now, if you want to identify reliably what type of incipient fault is present in the transformer, remember, you are not allowed to open up the transformer and inspect it, what is happening inside. The moment you open up a transformer tank, it's gone. It's a hermetically sealed chamber, so you are not allowed to open the transformer up. You can only take out sample which does not disrupt the normal process of normal operation of the transformer, like sampling of gases, sampling of oil, and a subsequent testing of it, but you are not allowed to open it up. So if suppose multiple faults are existing and that is actually generating gases which is not easy to interpret, then what should be the solution of identifying the faults which is present in the transformer? The obvious way is to use all the gases which have been identified by the gas chromatography and using some kind of ML technique to find out the relation about these gases getting generated in this proportion. So this must be associated with this kind of faults. But the problem is, the more number of independent feature you use for, that means essentially the gases which I am dealing with, all these gases will act as an independent feature which needs to be inserted as inputs in a machine learning technique. So the more independent features you use, the more computation intensive will be the training. As far as deployment of this particular trained networking field is concerned, that becomes a little bit difficult. Please remember, as far as research is concerned, as far as theoretical research is concerned, it's not an issue. Instead of considering 10 gases, you can consider hundreds of them. But if you're trying to deploy it in the field, then the computation needs to be manageable in amount. So this brings us to what is known as principal component analysis. So principal component analysis, what it does, it actually maps the entire feature space into a subspace which has lesser number of independent features. Okay, so it's not a predictive ML technique and it cannot be used for classification purposes. However, it can be used for feature extraction and identifying which component of the independent features that we are talking about can be used for proper classification. So in order to show you the advantage of principal component analysis, let me first explain what this thing is. This is known as what is known as a Duval's pentagon. So you can see on the left hand side, you have a pentagon with different gases marked over here, H2, C2H6, CH4, C2H5 and C2H2. Okay, I am basically considering the center to be 0, and if you consider any one of the axes present, suppose from 0 to C2H6, the terminal point is 100% and the center represents 0% of C2H6. So if you consider sampling of a particular oil and then testing it subsequently, suppose you get 23% C2H6, 15% H2, 9% C2H2, C2H4 is 18%, and CH4 is 35%. So essentially, if you connect these points up, you will get a irregular pentagon. Now, if you are considering an irregular pentagon, then essentially it is possible, mathematically at least, to identify the centroid of this irregular pentagon. Now, the moment you identify the centroid, it will have an X and Y coordinate. Now, if you put this X and Y coordinate value in the map shown on the right hand side, you should be able to identify what type of fault I am dealing with. See, this S represents stray gases. That means it's the transformer operation is normal, no fault is there, only some kind of stray gases are getting generated, which is not indication of any fault altogether. T1, it can basically is considering T1 to be spanning this kind of an irregular area. So if the centroid of your fault shown on the left hand side by this red dot is actually lying within this T1 area, then I will be classifying that this particular transformer is having this T1 type of fault. T1 is basically low energy thermal fault. So on and so forth. So ideally, if you have oil samples, using this Duval's pentagon, you should be able to identify what type of fault I'm dealing with. But in reality, this is not the case. See, what I have done over here, I have considered data related to dissolved gases from IEEE data port data. This is freely available. IEC Technical Committee 10 data. This is also freely available, and some real life data. So what I have done then, I have actually found out the centroid of the pentagon, and then I've plotted it in Duval's pentagon. Ideally, you can see these different colors represent different type of fault. Each color should have been confined to a particular area, which is not the case. So this implies that if you're only considering 5 gases instead of all the other gases available, you will not be actually properly classifying the fault which is happening inside the transformer. Remember, my whole purpose is to identify what type of fault is present inside the transformer so that I can take preventive action, and in the process, I can extend the remaining useful life. But if the classification cannot be done properly using the raw data that I'm getting, so that will create problem, because the preventive actions, whatever I will be taking, that will not be effective in addressing the problem. And as a result, the RUL will not be extended. It can be even reduced to a certain extent. That is the problem that we are dealing with. Now, the next problem that needs to be considered here before we go further is that, see, what is our constraint? We are not allowed to open up the transformer to inspect what type of incipient fault is actually present. We are only trying to predict the incipient faults which are present in the transformer by an indirect assessment, by analyzing what type of oil gases are present in oil or not. Because this constraint is there, so you don't have a control set where you know, or training set where you know this is the fault which is existing and this is the gases which has been generated because of this fault. So that is why even if you consider multiple sets of data, you will never be getting a database which has equal number of data points for each of these 6 categories. And until and unless you have a balanced training data set, you will not be able to use it for any kind of machine learning technique, because that will give you a biased training. It will be actually predicting in a very good manner few faults or few features, but whichever point is scarce in number during in the training data set, it will not be that effective for that category. So this brings us to the application of what is known as SMOTE, synthetic minority oversampling technique. So what it does, it first identifies 2 nearest neighbors for the class which has lower number of samples. And then the distance between, so for example, if you consider x1 and x3 over here, it synthetically creates this synthetic data point shown over here by the red dot and marked small a over here. So it essentially just generates a point somewhere in between 2 data points belonging to minor data set. So in this fashion, what we have done, we have made a balanced data set for further processing of these gas problem. So then what we have done, we have plotted each type of fault within the Dual pentagon itself. Okay, then what we have done, we have actually identified the cluster which can be considered as a boundary where all the points pertaining to a particular fault will lie. And for that, we have used what is known as density-based clustering. So it's another technique where we actually considered that 75% of all the data points, the area of this cluster will be designed in such a fashion that 75% of all the data points which have been used for identifying the said cluster will lie within the cluster. And the rest of the 25%, which will be lying outside the cluster, will be actually considered as outlier and will not be considered as influential data points. Okay. There is a reason behind doing this, because see, if you are taking out samples for testing, especially for DGA, there are certain IEEE IC standards for doing so. You will have to take the oil samples at a particular temperature. You will have to sample it in a glass bottle. You will have to seal it. You should not be allowing any kind of contamination to enter into this oil sample, and so on and so forth. Now, in a lab where all the proper precautions are taken, it is very easy to maintain this standard. But if you're talking about considering or sampling this type of oil from a field unit, then it depends largely on the expertise and the know-how of the person who is actually taking the sample out. So this creates many problems, and for that is the reason why certain outliers will be there in your data set. You cannot avoid it. Now, once the cluster has been defined, then we identify, just like the centroid of a pentagon, we identify the centroid of this particular cluster. And corresponding to each type of fault, we have identified a cluster, and we have then identified the center data point of this particular cluster, and we have used this as one of the features. Now, this is what we have identified. So there are 6 clusters. And depending on which cluster we are talking about, these are the centroids of X and Y coordinate. Now, we have used 11 features rather than in case of Duval's pentagon where we used 5 gases only. Here we have used 11 features. So as of now, we are not talking about any reduction of computational burden onto the classifier. Here we are only trying to identify which features must be selected so that the classification becomes successful. So Once you have identified the centroid of the fault point, then you calculate the distance between each of these fault clusters, centers. So this will actually generate these 6 data sets. Now here lies the advantage of using principal component analysis. So if you are talking about principal component analysis, what if the feature set is having 11 independent features, then there will be 11 principal components associated with it. Now each of these principal component will give you a sense of direction in which the variables is actually varying the most. For example, if you look at the left hand side figure, you can see that there are 2 features involved, and essentially these blue dots are the data point that I have considered. So you can easily see that these data points have a tendency of maintaining a positive slope with these 2 features. So essentially this pink color line gives us the direction in which the data is actually varying the most. So this is the principal component number 1. And the direction which is in orthogonal sense to this principal component 1 will be principal component 2, and so on and so forth. Now, interestingly, mathematically, it can be shown that only first 3 or 4 principal component needs to be considered. We don't need to consider all the principal component. And this is where the feature reduction or the dimensionality reduction of the feature space is coming into the picture. Now see, previously in Duval's pentagon, we have seen that if you plot all the faults together, it was creating a completely messed up picture. But if you are talking about these 11 features and then you are finding out the principal component and you are plotting the third principal component as a function of first principal component, you can easily see that a clear boundary can be defined which actually separates out the discharge from the thermal and PD fault. Okay, so using this equation which is shown at the bottom part, you can easily identify whether the fault is a discharge type fault or whether the fault is something else. Once that is done, now we are using the fourth principal component and the first principal component. Remember, the discharge part has already been isolated. So here we are isolating the PD from the thermal part. And finally, if you are considering third principal component, second principal component, here you can see that zone 5 and zone 6 basically separates out low energy thermal fault and medium energy thermal fault from high energy thermal fault. So what I'm trying to say is this: using only 5 gas concentration, we can generate 11 features which after application of PCA, we can transform into certain principal components which can be used with higher accuracy or higher reliability to identify and thus classify the incipient faults. Now, what will happen if this classification is not done properly? Because that is the main motivation which we started with. So I will not be going into detail of this because this deals with machine learning. See, if you remember this fault, this was actually classifying the green dots were low energy and medium energy thermal fault. The red one was high energy thermal fault. Now, on the left hand side, you can see the transition that is seen for a particular transformer over the years. That means previously, this 17 data point was actually in zone 5, which was actually representing thermal low energy thermal fault. But over the time, because no preventive action was taken, it has transitioned into zone 6, which represented high energy thermal fault. Now, internally, what does it mean? Low energy thermal fault means you are having a small fault where an arc is happening, but this arc is not generating that much amount of heat energy. Remember, whenever there will be arc formation, there will be carbon deposition, and depending on where this carbon is getting deposited, your insulation will get degraded. Now, because you have not taken preventive measures, so what happened over the time, this fault has changed to a high energy thermal fault. That means here also the arc is getting formed, but the energy associated with this arc is significantly larger. As far as the temperature is concerned, it is generating around 700 degrees with respect to previously, which was generating much lower temperature. So the impact on the insulation will be higher. There is another problem. I was telling you earlier that several factors are there. These are the problems that we had to deal with. There is another problem which is related to oil treatment. Remember, we need to reuse material. If the oil has gone undergone significant aging, if it is significantly wet in nature, then you need to treat it out. Once you treat it, that means demoisturize, degasify it, you are going to put it back into the system. The moment you put it back into the system, the original gas concentration markers, they are gone because you have treated it separately. That doesn't imply that the fault has vanished. The only thing that you have ensured is that that fault has not generated sufficient gas yet that can be identified separately using a gas chromatography. And that is happening purely because of oil treatment. So the mechanism needs to take care of that as well. That even if you have a oil treatment, it should be able to identify what type of fault that is present in the system or not. Okay. So this brings us to the end of the online technique that we are discussing today. So in case of online technique, we are going to have these kind of faults. So as my previous speaker was telling, cybersecurity risks will always be there, because think of it in this fashion. The location where you are testing this gas chromatography, because it's a costly equipment, it cannot be deployed in a large scale. It has to be present in a central facility. So you are going to send the sample to the central facility, and this central facility is going to test it, interpret the result, and then it is going to send the information back to where the transformer is located. This channel where the information is being sent, this might get corrupted due to intentional or unintentional problems that needs to be taken care of. So this brings us to offline test. Okay. Please let me know when my time is up. Okay. Hello.
Up to 9. Up to 90.
Okay. Okay. Thank you, sir. So this brings us to the end of the online test. That means now we are going to deal with certain tests which requires the unit to be switched off, isolated from the grid, so that the test can be carried out. Now, previously I told you that the online test can only give you information regarding certain aspects, but certain critical information cannot be obtained from such online tests, specifically DGA. I should not be generalizing it, because there are other online tests which has some other capabilities as well. As far as DGA is concerned, it can only give you information regarding the oil properties and the incipient fault, specifically these 6 incipient fault. What DGA cannot provide is crucial information like what is the wetness nature, or how much wet is the solid insulation we are talking about. What is the DP value that we have, the depolymerization value of the solid insulation that we have, or what is the moisture content in it, what is the remaining useful life of the solid insulation that we have. Remember, oil can be replaced, oil can be taken out, treated, and then it can be put back into the tank, unlike solid insulation, which is fixed over there. If the solid insulation has become extremely wet in nature, so what we do, we put fresh transformer oil inside it, and then we heat it up by either circulating a small amount of current or by some other means. So what it does, it actually increases the saturation, water saturation limit of oil, and as a result, moisture from solid goes or migrates into the oil. Okay, I am not going into the detail of that because that will take another session altogether. There is something called thermo-moisture equilibrium. Depending on what is the temperature of the insulation we are talking about, it has limits up to what amount of moisture it can absorb. So if the solid insulation becomes extremely wet, what we do, we put oil, new oil into the tank, heat the oil up by some mechanism, and then we bring out the oil demoisturize it, and then we put it back. So this to certain extent dries up the transformer insulation, which needs to be maintained in its pristine condition. Now, even if you do this, because of the complexity of the overall insulation that we're talking about, because the amount of solid insulation that will be present in a decent size power transformer will be few tons. So you can think about the situation that even a 2% moisture by weight for a transformer having 2 ton of paper is huge. That much amount of water needs to be taken out of the solid insulation so that the insulation integrity is maintained. But simply by circulating oil, this is not possible. So what is important over here is that you need to have certain parameters or performance parameters which you can use to identify what is the present state of the insulation, whether it is safe to use the equipment or whether it is very prone to failure. Okay, so this brings us to what is known as insulation response. So if you're talking about oil paper insulation, in an abstract sense, oil paper insulation is nothing but paper which is immersed in oil. So this basically behaves like a dielectric material. So if you think of a situation where I have a parallel plate capacitor, and within this parallel plate, I have inserted an oil impregnated paper, which is the method how you get this paper capacitors. Then if we apply a DC voltage across it, essentially it will behave like a dielectric material. So the response that you are going to get will be a monotonically decreasing current. Unlike normal dielectric, which has only one type of dipoles present inside the insulation, here we are talking about a very complicated dielectric material which has many types of dipoles present. So the response current that you are going to get will not be a purely exponential decay function, but it will be a monotonically decay function which can be approximated as sum of several exponential decay functions, each having unique properties or unique parameters. Now, depending on whether you are actually applying a DC voltage or a AC voltage with variable voltage and variable amplitude and variable frequency, the response that you are going to get will be either termed as time domain response or frequency domain response. Now, because we are talking about the same insulation, so this in transformation of time domain response to frequency domain response and vice versa is equally possible. So it doesn't matter whether you apply a DC voltage across the insulation and get the time domain response and then you convert it to frequency domain, or you apply a AC voltage source with variable frequency across the insulation, identify the frequency sensitive information, and then you transform it back to time domain. Both are possible. Obviously, with Nyquist rate of sampling, there are certain criterias or cutoff as far as the frequency information is concerned. Now, the lower half of this picture is a very interesting thing. We will be dealing with this later on. This is something dealing with freed charge carriers. Now, there are different type of polarization which can occur within a dielectric material, like interfacial polarization, electronic polarization, ionic polarization. Another polarization happens, which is known as hopping polarization. So this essentially is charge particle, because see, within this oil, the oil is continuously in motion so that it can take away the heat getting generated in within the hot part or the live part, and it can radiate it in the radiator fan. That is the whole process, or that is the primary utility why we circulate oil in the first place. But because this oil is in contact with the solid insulation and it is continuously in motion, so what happens, certain charge carriers gets absorbed at the surface of this oil paper interface, and over time what happens, these charges will quote unquote hop from one position to another position, and in this process charge migration takes place and kind of a polarity develops. This is what is known as hopping polarization. This is very slow in nature, even slower than interfacial polarization, and this creates lot of problem. Okay, so I'm not going into detail of this. This is just the set up how we measure polarization, depolarization current. So you can see on the top right corner, you have the test object, which will be actually assumed to be a transformer insulation. By the way, these tests are all offline in nature. You can understand that I am specifically applying a DC voltage across the insulation. That means I am isolating the switching the transformer off, isolating it. Then I am actually applying the DC voltage, not to circulate DC current through the winding, because that will be leading to saturation and will create on its own problem. But what I'm doing, if you consider the left, I do have a picture with me, I think. Yes. So if you see the middle figure, you can see the left, the live low voltage insulation, a low voltage winding, which is shown by this gray rectangle, has two terminals. So what I have done, I have shorted these two terminals. Then I have actually designated this to be electrode 2. The same thing I have done with the high voltage winding. So if I am applying the voltage between electrode 1 and electrode 2, you can understand that both the starting as well as the ending of one particular winding is getting maintained at the same potential. So DC current is not going to flow through them, through the winding. However, DC current is going to flow, in a sense, perpendicularly through the from low voltage winding to high voltage winding, thus encountering the insulation which we were talking about. So this is what the test object is all about. At the very start, what we do, we actually connect this U0, which is the DC voltage, across the test object through an electrometer. Electrometer is basically an ammeter having very low current measurement capability in the range of 10 to the power minus 18 ampere, because we are talking about insulation over here, and insulation by design is going to have a very high impedance. So if you are trying to measure a current which is actually getting generated because of a voltage, suppose 1000 volt DC, the current will be in the range of few microampere or nanoampere. So you need an ammeter with the capability to measure accurately at that small level, and that is why we use picoammeter or electrometer, because it has very low current measurement capability. So typically, polarization and depolarization current. See, this is important. Once you have applied the voltage and you have recorded the monotonically decreasing current, what is happening inside the dielectric material? That is going to have dipolar energy present, because we're injecting the energy in the first place, and that half CV square, which is present within the insulation as dipolar energy, must be dissipated before it can be put back to use. And that is where depolarization comes into the picture, where you just bypass the source and you short circuit the charged dielectric onto itself. So that generates another current. The dipole goes to the initial position, and essentially the dipole relaxes, and you have what is known as a depolarization current. The problem with polarization, depolarization current is that typically polarization current is measured for 10,000 seconds, and dipole is measured for another 10,000 seconds. Now, 20,000 seconds should be, or generally is required to measure the overall polarization, depolarization current. For this entire duration, the temperature at which the ambient temperature needs to remain same, and the transformer needs to be in switched off condition. For 20,000 seconds, there is no fault in the transformer, yet for testing purposes, the transformer needs to be kept in offline mode. This is not a very acceptable clause or acceptable reason for the transformer operator, because for them, switching off a transformer is equivalent to losing money. And that is why you need to develop methodologies which are offline nonetheless, but they require lesser amount of time. Another problem is that there are two types of transformer that are generally used, either wet type, which are typically the power transformer that we use, or the dry type, because these transformers are used very close to urban areas where populations are there. And because of the explosive nature or flammable nature of transformer oil, we cannot deploy oil type transformers. So dry type transformers are also present somewhere in some cases. The problem is that if you're dealing with oil paper transformer, and dry type transformer, both of the insulation in both these two transformers are dielectric material, but the dipoles which are present in each of them are different. So the response to DC or variable frequency AC for these two type of transformers vary. So yes, this is what I was talking about earlier. Now see, if you are talking about a parallel plate capacitor and you are connecting a DC voltage across this, then the current which will be flowing through the dielectric material will be a monotonically decreasing current or polarization current, which is mentioned over here. Once the polarization process stops, then you switch off the, disconnect the DC source and you short circuit the charge parallel plate capacitor onto itself, then the discharging current is going to flow and this half CV square energy which is previously stored is going to dissipate and is going to circulate a current through the insulation. Whatever amount of energy you have actually injected into the system during the polarization phase should be exactly equal to the amount of energy which is uh, given up by the system during the depolarization phase. That should be the case. But that is not what we found when we tested several real-life transformers. So what we have seen is that polarization current and depolarization current actually had significant distance difference in levels either throughout its span or during some of the ranges for this entire duration. So that implies that there must be some kind of energy source present in addition to the DC voltage we have connected to the dielectric material, which is generating this excessive current, this excess current, which is measured by the electrometer. Remember, the electrometer is connected outside the insulation. So the source which is present within the insulation is not going to be isolated, treated in a different manner from the source which is connected externally to the insulation. So as far as the electrometer is concerned, the dipole polarization current as well as the spurious current which is generated internally will be combined together and will be shown as the response. This is what we were getting. The only way how this excess current is going to get generated is by movement of trapped charges. So what happens is that whenever you have relative velocity between solid and liquid insulation, rather whenever you have relative finite velocity between two insulation which has difference in conductivity, then an electrical double layer gets formed at the surface. Electrical double layer is nothing but dipoles aligned just on the surface of this oil paper interface. And typically the negative part of these dipoles will get attached to the solid interface and the positive part of this dipole will remain free and interact with the moving oil volume. Now, if the speed of the oil is sufficient, then what will happen? This oil, positive part of this aligned dipole will be stripped away by the moving oil and will be ultimately taken with the flow. Now, because this oil is in contact with the grounded tank, so the positive part of this dipole separated out will be grounded and neutralized at the tank, but the negative part will remain in the solid insulation. And this is the trapped charge carriers that we are talking about. If due to lattice vibration or hopping polarization, these charge carriers become free, they get absorbed at the electrode and essentially contribute to the insulation response. So I'm not going into the detail of this. I will be providing you the presentation so you can look at it. This is important because see, the stripping away of this particular positive part and the negative part getting attached to the solid part, this happens at localized imperfections. Now, cellulose material is a polymeric chain. The degree of polymerization basically represents the number of monomers which are repeated in a polymeric chain. Typically, for a cellulose material, it starts from 1000 to 1200, and over time it reduces. That means what? Essentially, you are talking about a monomer getting repeated several times, and two monomers are connected together by some kind of bond, right? So what happens over time due to heat and continuous operation, the bond between two monomers break away, and that reduces the dp value. But the site at which these two monomers were previously joined, that particular site act as traps where these negative charges gets attached to. So as aging increases with time, the cellulose bond, that means the number of monomers present in a polymeric change, that breaks away, and that creates more traps. And as a result of these more traps, more number of negative charges get trapped, and thus the amount of effect that these free charges have on the port PDC, that increases. So that means the detrapping current, which is the current generated by these free detrap charges, that increases over time. So this is important because if you have detrapping current, that means the current which is measured by the electrometer. If by some means the method, I have skipped actually the theoretical part, it's present in the presentation, which shows how you can isolate the detrapping current from the polarization current. If you integrate the detrapping current, you will get what is known as detrap charge. Now this is very interesting because the charges which gets freed very quickly, they tends to affect the portion of the response which is closer to zero. Now, the dipoles which are present in oil, you can understand, but because this is a fluid, so the amount of time it takes to orient in the direction of applied field is smaller in comparison to the dipoles which are present in solid insulation, because they are totally bound together with each other. So the mobility of dipoles present in oil is much faster compared to the solid insulation, which in turns actually gets interpreted in PDC mechanism, where the lower part, that means that when time is very small, typically less than 100 seconds, the response typically corresponds to the condition of oil. As time increases, typically about 1000 seconds, the current actually, the response actually correspond to the condition of solid. So if you have detrapping current, you integrate it, you find out detrap charge. Depending on whether this detrap charge is from a shallow trap or deep trap, you can use this information to identify either oil properties or paper properties. If you look at the very last row over here, you can see that oil conductivity, oil moisture, activation energy, paper moisture, paper active conductivity, all these parameters can be obtained, which was inaccessible when you perform DGA. So here you can see paper moisture and detrap charge. So the detrap charge and paper moisture maintains a well-defined relationship. These black dots represents data obtained from power transformers, and these power transformers are located throughout India. So it has not been taken from one particular region. It has been taken from several utilities. The rating of the transformers varied from 100 MVA, 167 MVA up to 300 MVA. And yet all of them showed this definite characteristics where the paper moisture could be obtained using the detrap charge information. The same is true with the oil conductivity information. The oil conductivity can be obtained using the shallow charges. Remember, commercial equipments are available which are capable of identifying paper moisture, oil conductivity. So one equipment is specialized in identifying paper moisture, one equipment is specialized in identifying oil conductivity, and so on and so forth. However, if you go for insulation response analysis that I am showing over here, using one particular PDC test, you can actually evaluate so many parameters altogether. So that will require less amount of equipment, less amount of money, and efficient use of the resource as well. So the main problem with this type of detrapping charge related analysis is that you need a measurement of 20,000 seconds or more. Until and unless you have 10,000 seconds of polarization current, 10,000 seconds of depolarization current, you won't be able to find out the detrapping current, and as a result, you won't be able to find out the paper moisture, oil moisture, so on and so forth. Now, what is wrong with it? if you think of it from a practical point of view, measurement carried out for 20,000 seconds is not that high of an ask. But the main problem is you are doing this measurement at the very site. If there happens to be some change in atmospheric parameters, which changes the ambient temperature or humidity for that matter, the entire measurement will be useless. So that implies that we need to use the advantage, need to use the advantage offered by the detrapping charge, but the measurement time has to reduce. So this brings us to some of the techniques that we have used, where the amount of charge which has been injected into the system during the polarization phase and the amount of charge which has been um, received back from the charge unit during depolarization phase, we have considered the difference of these two. It has been seen that it basically follows one particular type of series, so on and so forth. But what is important over here is that we have managed to reduce the 20,000 second measurement to a duration of 1600 seconds. That means 800-second polarization current and 800-second depolarization current. So significantly, the amount has been reduced. So this is another problem which needs to be taken care of, because if you are measuring something in the field which is sensitive to temperature, you can't be assuming that the temperature during our measurement, whether it's for 800 seconds or 1600 seconds or 10,000 seconds for that matter, the temperature will remain same. If the temperature varies, what will be the criteria, or what will be the compensation technique that needs to be also offered? Remember, we are doing all these things. We are complicating the analysis part only to have a reliable information regarding what is the present state of insulation, so that we can take preventive measures and extend the RUL of it. Okay. I'm not going into the dry part of it, the oil paper insulation. This is the samples that we have tested in the lab. Because see, when we are designing any kind of technique, we'll have to first test it in a scaled down laboratory model. Then we need to apply it to real life equipment. Obviously, because we are actually testing the sample in a controlled environment and it's a scaled down model. So whatever parameters or coefficient of a particular equation that we obtain, that will not be applicable directly to a real life equipment without modification, but at least we know the nature, how the relation is going to hold between the parameter that we want to study and the diagnosis, the insulation response that we are obtaining. So these are the samples that we have used. This is just the FDS measurement setup, because up to now I was only discussing about the time domain measurement. We can also do the frequency domain measurement, where the frequency of the exciting voltage is going to vary with time. The amplitude is also going to vary, and essentially that will give us some information regarding the frequency sensitive information of the insulation. Here I must elaborate a little bit more. See, if you are talking about a parallel plate capacitor or any dielectric material, it will be basically behaving like a capacitance. And the capacitive reactance offered by this particular dielectric material to any AC voltage will be 1 by 2 pi Hc. So if the frequency increases, the 1 by 2 pi Hc part, this entire capacitive reactance decreases. So if you are trying to measure the dissipation factor, for example, dissipation factor tan delta, as a function of frequency, and the frequency is typically varied from 0.1 millihertz up to 1 kilohertz, you can understand that if you are increasing the frequency very much, that means the amount of impedance offered by that particular insulation to the applied voltage is going to reduce. So as the frequency increases, the amplitude of the exciting voltage must also be reduced. And that is the main problem with FDS measurement. You need a variable magnitude, variable frequency voltage source. That needs to be amplified, and that needs to be ultimately applied across the source or the sample that we want to testing. So I'm not going to detail of this. This is primarily considering the noise that we have in the system. So I think I will stop over here so that we can actually have 5-10 minutes for question answer round.
Thank you, sir, for an excellent and deeply informative session. So participants, now we have opened the floor for question and answer session. So please proceed.
Hello. I think I would like to thank my senior in my lab, Dr. Rajit Baral, for delivering an outstanding lecture on transformer condition monitoring. So I am
Oh,
very,
thank you, thank you, thank you, Shomo.
I have no questions. I was just listening like spellbound, what I can say, to this excellent presentation. Thank you,
We
Rajit.
should not have any questions right now because it's dinner time for many of us.
No,
I
thank
have
you
already bothered many of you.
for an excellent presentation and deep insight on transformer condition monitoring, because we have been working in this field for more than 12 years, maybe 15 years now. Thank you, Originda, for delivering such a great lecture.
Thank you for having me.
So participants, if you don't have any questions, then we can close the question and answer session. So if you have any question, please. Okay. So I would like to request all the participants, everybody, to switch on the camera. We have to take the screenshot. Okay. Thank you, everyone. Thank you so much, sir, for your valuable session. Yeah, insightful
Thank
session.
you.
Thank you.
Okay, so can I leave
Yes, sir,
now?
sure, sure.
Okay, thank you.
So with that, we formally conclude the academic proceedings for day 2 of the faculty development program. So we look forward to welcoming you tomorrow at 6 p.m. for day 3 sessions. Thank you.